Aditya, you can start, I think.
Yeah. Okay, let's start. Okay. Hello, everybody. Welcome back, viewers. Welcome to another episode in our Explorica engineering series. Just give a small introduction about us for the new viewers here. So we're SkillShark. SkillShark is an edutech startup focused on imparting 21st century skills to the youth. Um, what differentiates us from the rest is our approach and motive to impart these skills, dedicated to making experts out of learners. Now, we're focusing on mainly the delivery of skill oriented services to educational institutes and the youth of these institutes. The skill gap is a major problem that India is facing right now, and the problem has just got aggravated with the COVID-19 pandemic and the long lockdown that's followed along with it. So all the sectors are continually evolving, and we're trying to prepare everybody to gear up for that when we all get back to a smooth road. So let's get back to the Explorica series. So in the past two episodes, we've had an introduction to motorsport, and then we also had the chance to have a session with our co-collaborators who are rev mechanics from the IIT. Now, this episode is not really going to be motorsport centric, but don't worry, it's still definitely a derivative of a superset, which is high-speed mobility. Now, for those of you who don't know, the fastest train in the world is the Shanghai Maglev train at the moment. Goes around 430 kilometers per hour. Just imagine a train or a capsule that goes nearly 3 times at that speed, faster than your standard Boeing Dreamliner. Yep, we're talking about the concept that Elon Musk first visioned about 8 years ago, and we have some very special guests with us today. I'd like to warmly welcome Avishkar Hyperloop, the official Hyperloop competition entrance from IIT Madras, on behalf of SkillShark EduTech and Rev Mechanics. Welcome to the stream, guys. Thanks for being here with us on this webcast. Can we start with a small introduction of each of you individually and just a brief overview of what each of you did or is still doing in the team?
Okay, so I guess we'll start with Suyash because
Yeah.
he's the founding father of the team. So Suyash, can you just go ahead?
Yeah, sure, Aditya. Thanks, Adut, and thanks, Skillshare, to invite us to this presentation or the webinar. Uh, so let me tell about myself first. So I am here. I am an alum of IIT Madras. I did my post graduation in aerospace engineering, and while I was in IIT Madras, I founded this team in Avishkar, and we actually got together in 2017. From there, we started the Avishkar Generation 1, and that was the time when we were into it. So I was the founder and team head that time, and I think Aditya.
Yeah, sure. So I'm Aditya Ranade, and just like Suyash, I've also been a part of the team since the beginning. So he was the founder. I was part of the first Avishkar team ever, and I've been part of this team for 3 years now. So in my third year of engineering, I joined, and uh, well, in the first year, I was a part of the design team. So essentially, everything that makes all the entire design come together. And the previous year, I was actually one of the team leads for the team. So when Suyash graduated, I had the responsibility of leading the team later on. And this year, I've graduated from IIT Madras, and currently I'm pursuing my MBA in Business Analytics at IIM Bangalore.
Yeah. Okay. I'm Neil, and I'm currently in my third year of engineering design department, IIT Madras. So I am the head of the team Avishkar Hyperloop for this academic year. So basically, I had joined Avishkar in my second semester. So I joined in the second version of the team. So I joined in around late 2018. So initially I joined as a business team member. So we used to take care of all non-tech stuff. So as in sponsorship, marketing, and all. So and then later on, before the competition, as there was need in all other subsystems, I started doing some technical work as well. So and in 2019, I was a part of controls and communication subsystem, and currently I am the head. Yeah.
That's great. That's great. So we have a good variety of both technical and management backgrounds from all three of you with the team, which is it's a really good combination of skills we have right now in this webcast because it gives us an overall picture of what this project is all about. Let's get back to the actual project. Let's start off with that. So this is basically a concept that was started off in theory back in 2013, correct? What Elon Musk came up with, and I believe the competition started roughly 4 or 5 years ago. So how did the team kind of get involved in this? When did that idea of getting involved start, and how important was it in the beginning stages of the team?
Right. So I was sitting at that also. All of the team members from Avishkar were contributing in some other project at that point of time. So we all had those kind of minds, and it was more of why our country is doing it, why can't we do it? And then the idea sparked, and we continued, and then we figured out this doesn't have a literature. I mean, this has got no internet search. I mean, even if you today go ahead and search about Hyperloop, that has hardly a bunch of research papers, nothing more than that. So that was a really tough task to put together a team and tell him, this is what you have to design, but you don't have a literature to understand what it is. And from there, the journey started pretty much. And so the couple of documents which we started were white paper, as you mentioned, which was done by Elon Musk in 2013. So that was one of the Bible for us to understand what Hyperloop is. But we come from interdisciplinary backgrounds like aerospace, mechanical, electrical backgrounds, and that really helped us to design every subsystem. And then we did a lot of system simulations, weight budgeting, and etc. And from there, we kind of kicked off to other things.
Right. Yeah, it's interesting you said that it's interdisciplinary, of course. So the entire vehicle itself is not just a vehicle. There's just so many different components involved, and I think that's really cool that you said the founding team was already involved in other student teams, which always brings that diversity. So yeah, it seems like a very great platform for everyone to get involved. It's really nice to hear about that. So definitely, we'll get back to exactly that, which is the different domains that are involved in this. How many subsystems you actually have in the team, and how is the technical team basically structured? And then if you have a corporate team, how does that kind of play into the project as well?
Aditya, you want to go ahead?
Yeah, sure, I'll take this. So when it comes to subsystems, this is such a massive project. It's not like everyone can work on every single aspect at all times. So essentially, we had to split it up into different subsystems. So especially for this pod, we had like a variety of subsystems. So we had starting it from the propulsion subsystem, we had braking, we had controls and communication. Then for the stability of the pod, we had the suspension and stability. Just for the chassis and the structure of the pod, we had the structures. Specific was the battery system or the power system. And again, we had another one for the business and the media and PR basically. So all of this, it's like all the subsystems are always in close conjunction with each other, but they also work kind of independently. So whenever one subsystem is working on its own, it's like the other subsystem would not interfere with them unless they are like, it's absolutely necessary that they're making some grave mistake or missing some important factor. So we had to split it up into these subsystems, and at the end, we had to just essentially combine all of them together. So the first iteration was a very rough iteration which we had, in the sense that every subsystem just had their own ideas in mind, and based on that they used to work. But then once the first iteration came together, we used to sit together, so all the team members at once, and we used to point out what are the flaws in one particular subsystem's way of thinking, or how exactly this subsystem should look like, because it will interfere with something else. And then it goes on and on. So after these inputs, there will be a second iteration. Then again, we'll sit together, we'll work on it. And then again, will be third iteration. And this used to go on. We had about 4 or 5 iterations of the pod before we were able to finally decide on the final design. So it's like, it took a lot of our time, but yeah, it was also worth it. Like working for like 4-5 hours a day. It's like, yeah, simultaneously balancing our academic life, lectures, assignments. Yeah, it is quite fun.
Right. Right. So roughly, what was the time scale for each iteration? How long did it actually take from inception to a final model that actually works?
So the first iteration is actually, I would say, the most difficult because when the first team was formed, no one had literally any idea about what a hyperloop is. So all we were doing, we were just like essentially playing chess in the dark. So any idea which we had, we would just like think about it. Okay, let's see if we can implement this. We'll use it in one iteration. We'll implement this, and again, there'll be some minor flaw which we used to get. So then again, we'd have to reiterate over it, get it in the second iteration. So for the first iteration, I'd say we roughly took about 2 to 3 weeks, but for every subsequent iteration, it was done roughly in 5 or 6 days. So as the complexity of it used to increase because the subsystems had to work together with each other, the time required for each iteration actually used to went up.
Right. Yeah. So, for the benefit of our viewers, could one of you actually explain what the Hyperloop actually is and what your prototype exactly does in it? What makes a Hyperloop special? What is it that makes it different from high-speed rail transport? And also, what sort of propulsion system do you use to accelerate it to the speeds that we're talking about?
Sure, Neil, can you take this?
Yeah, sure. Um, so Hyperloop is basically a fifth mode of transportation. It's called fifth mode of transportation because the current four modes are through railways, waterways, airways, and roadways. But Hyperloop travels in a vacuum, almost a vacuum tube. So in a near vacuum tube, you could say, because the pressure is like very less, around 1,000 of the atmospheric pressure. That's why it's called the fifth mode of transportation. And here we can achieve very high speeds because of two main reasons. As we'll be traveling in the vacuum, there'll be no air drag, and apart from that, even like the concept itself is proposed that it's that pods are going to levitate, so there will be no friction as well. So we are basically eliminating both the ways of resistance to travel. So yeah, that's why it can achieve such high speeds. And as far as feasibility is concerned, so Hyperloop is as cheap as roadways or bus or train, and it's as fast as aircrafts are, maybe more than that, depending on the distance between the two cities. So yeah, and so here we have a small comparison of how much it will cost and how much time will it take. So you can this is for the Chennai to Bangalore road. So here you can see that the cost is somewhere in between the train and the flight, and the estimated time of traveling is much lesser than even than the flight, because in flight there's some extra time for you have to check in before some particular time, and then yeah, but then nothing like that will be having here. So yeah, and as far as technicalities is concerned, so this was our first design. So we have 6 different subsystems in our design. So chassis is basically the whole thing on which we mount all our other subsystems. So propulsion subsystem is the subsystem which takes care of the propulsion, as the name suggests. And stability or suspension subsystem takes care of the vertical and horizontal suspension, because if you're traveling at such high speeds, we'll of course need something to keep it not make it vibrate more than some particular level. And here then we have power system subsystem, which will take care of powering all the different parts of the pod. And then we have control subsystem. So control subsystem basically takes care of all the controlling, as in giving the signal to propel the pod or break the pod or increasing the speed, and everything is controlled by the controls board over here. And then we have a pneumatic circuit. Pneumatic, it's basically a braking subsystem. So we had used pneumatic actuators for our braking subsystem. So that's basically about it. So in our first iteration, we had used normal electric motor propulsion only, and in our this is our so yeah, this is our second design, where we tried using electrodynamic wheels. So electrodynamic wheels are nothing but you know uh, here we have magnets. So these are basically the normal wheels, and then on those wheels we have magnets mounted on them in a particular hallback arrangement. So when the wheels rotate, because of the magnetic field generated due to the magnets, they induce eddy currents in the I track, as in the track metal conductor, and due to those eddy currents, there's a opposing magnetic field generated in the track. So because of that, two magnetic fields repel each other, and that's how we propel apart. So this was for our second design. So this was our first design was around, you can see the length of it. It was around 2.7 meters. So for a second iteration, we tried to reduce it by a huge amount. So our second iteration's length was around 70 centimeters, and so basically you can put this in a large suitcase, the whole pod in a large suitcase. So again, here we had different subsystems, and in our second iteration, basically we tried to optimize all our subsystems and try to reduce the weight and size of the pod. Yeah, that's about it.
It's really interesting to see the design and the build of your vehicle, especially the propulsion system. Like you said, you can either use the electromagnetic propulsion that you were talking about, and I also read online that some teams use pure pneumatic propulsion as well.
Yeah.
What are the advantages of both? I would guess perhaps the major disadvantage with an electromagnetic system is the weight of the assembly itself. Right?
Um, okay, not necessarily, because here so what we did here is basically we have motors and we have wheels mounted to those. So yeah, for these wheels, like initially we had motors which were very big, but then as we were propelling, because of the uh, repulsion in the magnetic fields here, we didn't have to use such high power motors. So we chose very small motors which you can use even in drones. So because of that, we reduced the weight here. And as far as pneumatic propulsion is concerned, I think that will weigh higher than this, because we need to store the gas in the big pipe and big cylinder maybe. So, and the main problem with that pneumatic subsystem is that it increases the size by huge amount. Like, it requires a lot of space. So yeah.
Right, that's interesting. So it's basically more efficient at the end of the day in terms of power loss, correct?
Right.
And it's interesting that you use an aerodynamically shaped shell. You had mentioned that the tube itself, the hyperloop itself, is it's in near vacuum, right? So how much of an effect does an aerodynamic shape actually have in terms of stability and drag reduction?
Okay. Aditya, do you want to take this, or do I go ahead?
Yeah, sure. So essentially, the thing is, it's not a complete vacuum when it comes at the end of the day. So there's still some partial air pressure inside, because you cannot, it's not that easy to completely vacuumize something. So zero atmospheric pressure, it's possible, but yeah, the expenses will be quite large. And again, when you're traveling at speeds close to 800, 900 kilometers per hour, and the cross section of the tube compared to the cross sectional area of the pod, if it's quite comparable to each other, then you get kind of like a sonic boom effect at the end. That the air keeps building up, the air pressure keeps building up right in front of the pod, and just towards the end, it all gets released quite quickly. So that is what we wanted to avoid. So that's the reason we went for an aerodynamic shell. In fact, this shell which you see on the screen right now, it's actually inspired by the Tesla Cybertruck. So that was actually rolled out quite about 2 to 3 weeks before we actually started to design the shell. So it was inspired by that, and that is how we decided to go ahead with it.
Right. So I would assume that your competition primarily tests the ability for it to accelerate with a safe amount of G-force, and then would they also check the top speed? Or could you run us through the objectives of the competition and what exactly they judge you on at the end of the day?
So,
Yeah,
Right. So the competition actually doesn't matter. I mean, doesn't worry about the G forces. There's no human who is sitting on the pod at the end of the day. So it is all about propelling it to the highest speed in the lowest amount of time, and that's what is the criteria to win uh, at the end of the day. But before that, we have 7 days of testing week. So a complete week of testing where we have to demonstrate each subsystem individually. For example, power systems, we have to demonstrate how safe we are in terms of power systems. We have to demonstrate what is the level of charging and discharging our batteries are doing. How are they behaving in backup? How are they, uh, what is the kind of monitoring that we can do on top of our batteries? Similarly, are we able to put brakes? Are our control systems working on time? And several other sensors are working fine or not. So all these things have to be, undertaken while we are testing in Los Angeles that week. And that is where, because it was the first time for us and all other teams who were in top 10 besides us were the returning teams. And what happened was one of the components failed because it was not failing, but SpaceX have such high standards, they wanted data sheet for everything. Right? Now, we didn't have that data sheet because we went to the local market, bought that, and put that into the pod. And that is where we lost one complete day. And that is why we couldn't, take it to the finals in a way we think. So, there's a whole lot of criteria. They have a very, very big rule book, which we have to go page by page. There are, I think, 14 to 20 sections. Some of them are applicable to some teams, like you mentioned about the pneumatic propulsion. Some of the teams are demonstrating levitation. So few of the sections doesn't apply to few teams, and they apply to others. That is how it happens. But there are 14 mandatory sections, as far as I remember, and they have subpoints. So in total, we have to go through another 110 tests before we make it to the final queue.
Interesting. So you have to first clear a certain number of gateways before even being allowed to go international and go to Los Angeles, right?
Yeah,
right. Yes.
I'm only talking about when you reach Los Angeles.
Okay,
Before
once you
that,
reach,
it's a
right,
whole lot. Yeah, yeah.
right. Coming to that, I heard that there were almost about 15 to 1600 different entrants in terms of concepts when the first competition came out. What sort of procedures did you have to go through to be one of the only teams from India to represent your design? What was that process like?
All right. So, we don't know what 1500 concepts were because it's completely with SpaceX. But
Right,
what
yeah.
we did is, uh, in our first attempt, we had this really futuristic Hyperloop concept that we presented to SpaceX. There were some issues with that. This is the successful design as we were showing in the presentation. But before that, there was one more design zero, I would say,
Mhm.
which was not successful for in our first attempt. But a couple of us, like me and Aditya, we managed to go to the US and find out what other teams are doing in 2018. Yes, in 2018 summer, and then we came back and we now had the complete know-how of the competition because not other teams who were participating from India or abroad were posting enough on social media so that you get to know what exactly is happening. And that is what another motto of Avishkar is to make people aware, without actually you paying for a flight ticket and going to the competition and seeing it. So we did that and then we came back, and that is how we saw that okay, there are 3 rounds to it. First of all, it is preliminary design round. Second is final design round, and third is testing, and then finally you get to run the pod. So first one was really okay, because it is more of a presenting your own concept. They all see the level of detailing that you do. So we ensured we are designing to the nut and bolts. Really, we are not just putting to the in the air that okay, this is how it will integrate or no, nothing. We were actually telling that there'll be M2 bolts, M8 bolts. That level of designing we did in the first round itself. Second round to get through, because there are a lot of entrants to filter ourselves out. We tried to do a lot of testing, meaning there were several subsystems. So we did testing for batteries, cells. Our institute actually supported us even if we were not in the final round. Then still they supported us to buy a few components which we can actually test, and then there was some center of material testings. There we went and we tested our carbon fiber small part of the chassis, and that is how we cleared the second round, because we managed to bring in lot of actual practical results into the design, and then finally the final thing happened. So that is how we went to.
Absolutely, I think that's really interesting. Having spent many years in Formula student, I can also agree that most of these competitions always want you to show testing data, and they want you to show supporting documents. Like you said, even data sheets, it goes down all the way to the bolt to prove that your design is stable. Yeah, it's really it is important because all of these student competitions, they're these are student competitions. It is developed by all of us as students, and the top priority is obviously maintaining safety standards. So yeah, that's actually really cool that you included as much detail as possible to your supporting documents. I think that's a very well deserved way of being involved in the competition. It shows how wholesome your design actually is. Coming to the design, could you run us through the major milestones and the processes? Of course, you talked about the iterations, but could you give a little more insight, some more details, if possible, as to the steps involved in making a preliminary design and then reaching that first iteration?
Yeah, sure. So, as I said before, when basically when we started the team and it was the first time participating, no one literally had any idea of how to go through with it. So when we started, we were all like, "Yeah, this looks nice. This looks interesting. So yeah, we'll go through this. We'll start design, making the design with this. We'll include this in our design. We'll include that in our design." And so all of it was like it. At the end, it seemed too overwhelming. Sorry for that. At the end, it seemed too overwhelming when we were trying to actually make the design. So later, as I said, as Suyash said, actually, that at the end, at the first competition where we were actually present at the competition, we got a general idea of how the pod should be. So we looked at the 20 other teams that were over there. So we were just over there as spectators. So we went there, we saw the 20 other teams that were there. We got a good idea of what all things we should include in the pod, and an even better idea of what all things we should definitely avoid including in the pod. So in the first year we had a pod, so that pod weighed close to about 700-800 kg. It was about 10 it was about 8 meters long. It was a huge pod. So from there, from 700 kg, we brought it down to 120, and that is because we started looking at the basics instead of just looking at the entire picture as a whole. So the chassis which you see over here, that's a complete carbon fiber chassis. And when we actually took the pod over there, we were the only team to have a complete carbon fiber chassis. Yeah, it was expensive, but that was something which we didn't want to avoid. So the chassis, as it has to bear the brunt of the entire weight of the pod, we wanted to make sure that we have the best chassis that possible. So we went with that. Again, it comes to the power systems, the battery packs, the cells, everything. We had to go through a number of combinations. So the number of cells, which cell, what should be the capacity of the cell, what should be the discharge rate, everything. Coming to the pneumatic circuit, the brakes. So you can see we have actually 6 brake actuators on the pod. So we had about 5 to 6 iterations where we went from 6 brakes, or then we went to 4. We initially had 8, and again. So at the end, it was all about reducing the weight of the pod without compromising on the speed. So since the acceleration is what determines everything, the mass of the pod had to be brought down to reach a higher speed. And again, at the end, it was all like, yeah. So everyone was essentially, when we came to the last final stages of the design, so during the final iteration, basically everyone had an idea of what all things are on the pod and how the pod is working. So if we reduce the weight of one particular component, how it will affect the other seven subsystems, or essentially how their own subsystem will be affecting the other seven subsystems and all of that. So yeah, that was actually an easy task when it came towards the end. But in the initial 3 or 4 iterations, yeah, we had to sit together a lot and brainstorm over all of this. I think you're muted.
Yeah, yeah, yeah. It's interesting to hear about the way in which you look at every single part individually and then put it together. Of course, for example, when you're designing components, you'll do FEA. If you're looking at aerodynamics, you'll use CFD simulations. Now, I have experience with Formula students, so I'll try to create an analogy to get a better understanding. So when we test our vehicles, we try to use lap time simulation software, or at least basic Excel sheets and documents to figure out how much time we're going to gain. Do you use a similar process to virtually understand how this runs on track? Do you have some sort of software that can simulate this, maybe using multi-body dynamics or something similar to that?
Yes. So as I said, the chassis is a carbon fiber chassis. So we had to go with ANSYS for simulation of that. And so essentially, it's like how carbon fiber works is the orientation of each carbon fiber layer is what determines the properties of that particular layer. So let's say a 90-degree orientation may be good for a normal stress, but a 180-degree orientation will be good for shear stress. So we had to imagine, so we had to orient each single layer depending on how we want the properties of the carbon fiber chassis to be. So specifically for that, we were using ANSYS for simulations. And again, when it came to the controls, when it came to the ESC and all, so we also had a brilliant sponsorship from ComSol. So whenever we wanted to simulate, so we had plans of using the linear induction motors as well. So for that, we were again thinking about ComSol. We had sponsorships from them. It was easier for us to simulate. Multi-body simulations, we used Adams. And since the Institute workshop, so the place we worked out of, it's called a Center for Innovation, and there are multiple student teams all working in there together. So it has a workstation where the institute had given us access to all these softwares. So it was quite easy for us to simulate it. And yeah, essentially, the simulation part was something which didn't hinder us because the softwares are generally not easily accessible at sometimes.
Yeah, and just to add to Aditya, when we actually started by building the concept, so we had to go through this, designing the kinematics and how the velocity will be achieved and all these things. So and as Aditya mentioned about different softwares for different subsystems, but there's no software unlike or like Formula One people have. For example, they have to minimize the time over the circuit whenever they go round and round, right? But for Hyperloop, it is nothing like that. So what we have to do is we have to build the a bunch of codes which came together, actually putting a lot of I would say a convex optimization method, which actually involved a lot of other power constraints as well as mass constraints. And then a few of us actually wrote that code in full, and we simulated it for a couple of days. And from that code, we started to build our subsystem. That was the most optimized, parameters that we found.
Yeah, perfect. Yeah, that was what I was specifically talking about as well. Yeah, it's like you have some sort of a preliminary control system along with the individual software that you use for designing the components, of course. Yeah, it's like using that preliminary iteration and constructing it virtually. But yeah, that's really interesting. Now it's kind of given a much more wholesome picture of how everything comes together. We talked about sponsorship, which is interestingly the next topic I wanted to cover. Surely a project of this magnitude needs a lot of solid financial backing. Understandably, just as a real concept, like even the real Hyperloop concept is projected to be a very expensive venture. So what sort of support did you get? And could you, if possible, you don't have to answer this, but if possible, could you give a rough estimate of what sort of budget constraint you had?
Neil, you're on mute.
Right. Yeah. So, sponsorship. Okay. So initially, our institute helped us. So, as Aditya mentioned earlier, we work at an organization called, it's a student organization called Center for Innovation, where all other student teams also work. So they basically have some budget, and then they allot some budget to each student teams. So we got some of our budget from there, and then we also approached, our alumni, and many industries for sponsorship. So we also got a lot of support from our alumni, and also, and our even our advisors helped us a lot in getting sponsorship, because the sponsorship we required, as in the total, budget was around 1 crore. And so yeah, we required a lot of help, and uh, our alumni supported us. As I said, as I mentioned earlier, even our institute supported us. So initially, that's because we didn't have anything to test upon or start with. That's when our institute supported us, and then gave some money to get some components and start testing. And then slowly we started approaching some industries, and yeah, we pitched them based on the design. And yeah, that's how we started approaching industries. And not just cash sponsorship, we also got kind sponsorship from many companies, like Comsol. As in Comsol, they gave us money as well, but they gave us the software as well, which we used for simulations. And other companies like Melasta. So we used Melasta cells for power systems, our power system subsystem. So yeah, so all these, some of these, sponsors, they gave us kind sponsorship, as in they used to give us some profit on the components we bought, as in 50% or 80%, something like that. So that's how we got the money to build a prototype, and kind of kind sponsorship, which helped us to build this prototype. Yeah.
So I may add, Neil is being a lot lenient actually. He didn't tell you the challenges,
Right.
So what happened was only 3 months, only 3 months, and we have to procure a lot of components from abroad, and we also have to raise 1 crore. So raising 1 crore plus 50 to 80% of the components coming from abroad is something which we had to manage, and that was really the toughest point, I would say, when we were in. And with the help of all of our team members, excellent coordination, plus a bunch of great advisors, we were able to manage to raise the funds and simultaneously put orders, because one shipment was going to come from Czech Republic, one was coming from China, one was coming from the US, and this is how we were able to manage. So I think Neil is being really lenient, but it was not that easy, as it looks.
Yeah, absolutely. I've got to say, like, great job for putting up all that stuff together. I mean, yeah, all these projects, even at such a small scale, you see how much it's actually amounting to. That kind of really brings the question how much, and it actually puts things into perspective as to how much it would cost to scale this up. Which is why we've reached the penultimate question, and we'll need to get through this a little fast, but it's a detailed question. I hope we can fit this all in. When you look at the scalability, your vehicle is a prototype, and it's a benchmark for a potential full scale test in India. What would be the technical differences between your prototype and the real model? Excluding the obvious differences of size and power requirement, and also to club that. We have seen we have seen Hyperloop One by Virgin Mobile. It's started off as a concept, and they're working on that. And India was one of the case studies. We also saw that a Mumbai Chennai corridor and potentially a Bangalore Chennai corridor were some of the case studies. And we also saw a bit of work going on, especially between the Mumbai Pune corridor. How much do you think you will be able to contribute to that? Or is your team actively involved in this, and are you having some sort of a real time involvement in this long term project?
Okay, so in 2019 July, we went to SpaceX for the competition, and we actually reached there about about 10 to 12 days early. And Virgin Hyperloop One had actually invited our team over to their headquarters in Los Angeles as well. So it's like they wanted an opportunity to get to know the team better. And so essentially, it's like, how would I put it? They knew about the work we were doing, and we knew about the work they were doing. So there was some potential overlapping in the sense that the technologies that we had actually planned on researching and we had actually planned on implementing were kind of similar to what they were thinking of doing. But when it comes to like a full scale, it won't be that easy because Avishkar Hyperloop is a student-run team and it falls under the overview of IIT Madras. So Virgin Hyperloop One, when they're planning on doing, let's say the Bombay to Pune corridor, it has to be with the Maharashtra government. So because of those issues, it's possible that there'll be a lot of hurdles in doing this. But yeah, I won't rule out the possibility of Virgin Hyperloop One collaborating with some Indian company or Indian venture in trying to do this. Second point, coming to the differences between a small scale and so essentially the prototype which we made and a large scale model of a Hyperloop. Obviously, the size is one of the biggest issues. And again, as you said, the power is also an issue. But apart from that, one of the major issues is, I would say, the propulsion mechanism which we are trying to use. So as you saw in the prototype, we use a brushless DC motor. So essentially, we had four wheels, they're being powered by four motors, and we were just kind of pushing it. So it's not that easy when you're talking about such a large scale, because at that level, the contact friction between the wheels and the track, it becomes significantly higher than what it will be at the prototype stage. So in the pod you're seeing on screen, it's about 120 kg the weight. And when you're talking about a full scale pod, it'll be weighing around 10-15 tons. So it's not something that will reduce the friction. Again, the aerodynamic design will contribute to it in reducing friction, but there'll be the air friction. You can't do anything about the contact mode. So one of the biggest challenges will be to develop indigenously a newer non-contact mode of propulsion. So just like maglevs, they're essentially floating on air because of the repulsion between the magnets. You also need something for Hyperloop. So one of the methods is a linear induction motor, which we have been developing. So our team has two research projects. One of them is the linear induction motor, and one of them is magnetic levitation or electrodynamic fields, essentially, I'd say. So the linear induction motor is something which we had actually planned on using in our first pod, but then we realized it needs a lot of work on it. So we have now classified it as a research project, which still falls under our team. And yeah, we have been doing quite a lot of work on it. So the linear induction motor is essentially a non-contact mode of propulsion where it's capable of generating massive amounts of acceleration. So the thrust which is being generated by linear induction motor is quite high than compared to conventional propulsion methods. Again, the second one is magnetic levitation or the electrodynamic fields. So as Neil pointed out before, in the pod which we made this year, we had implemented electrodynamic wheels. So again, that is a non-contact mode of propulsion, but it's slightly advanced than the linear induction motor because apart from generating the thrust in the forward direction, it also generates a slightly lower lift force. So it is also able to levitate your pod as well as propel it. Again, it's not yet completely developed. The work is still continuing on it. We still need to develop a lot of it. But this is something which will be one of the major differentiating factors between a prototype and a full-scale model. Another thing is the vacuum compatibility. So when you're talking about airplanes, they are traveling 35, 40,000 feet in the air. And it's not a complete vacuum outside. There's still some sort of air pressure outside. But when you're talking about a Hyperloop, it'll be like 1/100th of the normal air pressure or something. It'll be very low to be of any significance. So we need to make sure that the pod is completely vacuumized. It's completely sealed because even a crack or a single gap left between any two components will cause the air to just go out. Again, the acceleration has to be within the limits of what a human can endure. So it's not like you can give 4G of acceleration because it's not good for the human body. Again, when it comes to deceleration, you have to make sure that, yeah, the deceleration has to be within the limits. Another issue will be the track. So you can't have random curves in the track. You can't have instantaneous bends. If you want to go from, let's say, Bombay to Pune, the track has to be as straight as possible just to ensure that the pod doesn't have to reduce speed while going through turns or negotiating any turns. So these will be just some of the issues: passenger comfort, safety regulations. This is all something that comes towards the end after the technology has been completely developed, or it has reached a level where it's not easy to, it's not difficult to completely go through with it. Again, the braking system, the controls and communication systems, the power systems, as you've pointed out, will be a major differentiating factor because the power requirements for a pod of such a scale will be quite high. Apart from that, I don't think there'll be any significant issues apart just from, the building the track. The vacuumization will be an issue, but it's something that can be, it's not as difficult compared to construction of a pod of that size.
Excellent. Yeah. That was very detailed. Thanks. That was a lot of detail in one answer. And I think that's kind of really covered the major technical differences. So thanks a lot for that answer. Yeah, I think safety issues are probably going to be the biggest concern after this. It's just like when people first started flying airplanes, there was always a lot of tension in the air in terms of, well, literally in terms of understanding whether it's safe or not. There could be serious repercussions if there are any vacuum failures. But let's hope things really do stabilize. It seems like a very futuristic but still extremely efficient and potentially economic way of traveling. So yeah, it's great to see that you guys are constantly developing more as we speak, and hopefully we can see these actually implemented in real scale, and you all could be the ones that are really a part of this. Let's end this on a really inspirational note, and this is the question that I really wanted to get to. You had a team had the opportunity to interact and meet up with a person who has been a key player in automotive electrification, privatized spaceflight, and high-speed mobility on land, which is Hyperloop. What was your experience like meeting Elon Musk, and what are the key takeaway messages that he gave you? And I hope this could be a really inspirational answer for our viewers. Secondly, for our viewers, please do feel free to type in comments in the live chat in the YouTube on our YouTube stream, and we'll try to get through as many questions as possible after this. Yeah, and any of you can answer.
Suresh, I think you are the best suited to answer a question of meeting Elon Musk.
Oh, sure. I think we all met on the same thing, so probably not just me, but sure. That was something, or let's just say that is something that every young fellow would want to do at this stage of their lives. Meeting Elon Musk is something actually was a part of motivation to build this pod, to be very honest. And meeting him was a dream come true for all of us. And at the same time, when me and Aditya visited last time, Elon didn't interact with the teams that much, and we were kind of lucky to have a few interactions with him. So one of them was a public interaction where I was really fortunate to ask him a question. But we were in a fun mode because that was the last day in Los Angeles. So no emotional questions, nothing. So we all really went casual, and we were talking to him as if we are journalists. And we shooted a couple of questions. First one was this was also framed by Avinash, who was from our team. He asked the question when we were inside SpaceX and exploring what SpaceX makes, rockets and all. So he asked that, and I paraphrased it to Elon Musk that, will he be building coffee shops on the way to Mars on Moon? And then suddenly a big laughter came out, and in his typical way, he answered, "Sure, yes, why not?" And he just started talking about how to go Mars and all these things. So that was one first interaction. Then second was, when we we were kind of wrapping up for the day, and Elon was meeting several teams. So we got a chance. We all were, cheering for him because everyone was cheering for him. He was, and then he suddenly turned, and we started talking to each other. And again, in a fun mode, we asked him why not Tesla in India? Why is not Tesla? Where is Tesla? Like, why is it not coming to India? So he gave some answers, and then suddenly, he told some more things about several other regulatory issues, or what has some Asian issues. Asian governments have different way of handling Tesla. So he started talking about, and he gave some tips and all, also how he design, or how he thinks to make designs. And overall, one more interaction that I remember is he telling about, if you're wasting too much time on simulating things, then you're doing it wrong. That was the one message that we heard. A really, really very big thing for me, to be very honest. And that is the point, and that is the approach actually we took in Team Avishkar Hyperloop. We were always about experimenting, not simulating too much. And doesn't matter what kind of funds we had. And then we had a laughter and all, and then wrapped up. So quite inspirational for all of us. That was a dream come true for sure.
Sounds very exciting. I wish I could have been there. Yeah, I mean, coffee shops on the way to Mars. Who knows? Just a couple of months ago, he put manned space flight into action from SpaceX. So this could be a possibility. Let's hope by 2030 we're somewhere. And yeah, I hope all the viewers have also been inspired. I know I have. I hope this inspired all of us to get involved in these extra planetary and futuristic forms of travel. I'm pretty sure as soon as Hyperloop really hits the road, literally again, it's going to be like an entire sci-fi movie. You're probably going to get one step closer to Star Wars eventually. I don't think we have any other questions from the chat section. We have Rev Mechanics here. Amazing session, guys. We hope your team makes our country proud. Most of them watching got really good technical knowledge. Thanks, Rev Mechanics, for that comment. I don't think we have any technical questions from our viewers. So we have time. We have a little bit more time. Maybe one last question. Could you all maybe give an individual key experience that you can take away from your time in the team? Like, what's the first thing that you'll remember when someone asks you to talk about your team? This could be a quick 15, 20-second answer.
Go ahead, Neil.
Basically, I was the youngest in our team, like when we went to Los Angeles to represent India. So I was the youngest, and initially when I had joined, I didn't know anything technical. But then after I joined, everyone from the team supported me a lot. They helped me a lot, because of them, I was able to learn a lot more stuff. And yeah, meeting Elon Musk was, of course, one of the dream come true moments. And about that, I would say that after the competition, after the final day of competition, after we went back to our hotel, so all of us, just sat in a room, and then we were discussing about how the journey has been, since past 1 year. We are all working on it together and working so hard on it. So yeah, everyone was sharing their experiences, and that was one of the memories which I would remember forever, because that's when all of us shared our views and how the past year had been after working for so much time together. So yeah, I would say that was the biggest memory for me. Yeah.
So from my end, it's slightly different. So as I said, I've been a part of the team since the first year. And in the first year, we didn't actually make it to the finals over there. But it's like maybe the people in the team may have felt demotivated, but it's like no one was showing it out on their faces. So we got the results in February that, yeah, you're not qualified for the final stage. And we had our midsems. So we had our first quizzes, we had our exams at the end of Feb. And by the first week of March, we had again started working on the design for the next year. So the major takeaway, which I said, it's like even though we had not qualified for the 2018 competition, it's not like people were just like, yeah, this seems too difficult, we're not going to try it again. No, that wasn't the case. In fact, the next year we had an even bigger team when we actually tried to qualify, and that time we actually successfully qualified for it. So that minor 2 week gap between the mail that, yeah, you're not qualified for the final stage, and between starting work for the next stage, that 2 week gap was all that we needed just to bounce back and start working with new vigor. Again, the same thing happened at Los Angeles when we went to the competition at SpaceX. The competition ended on the 22nd was the final day of the competition. 22nd the competition ended. 23rd morning we were actually discussing plans on how to finalize a new pod. So we didn't even have an idea of if SpaceX is going to have the competition, what will be the scenario 1 year down the line. But yeah, it's like after just one single day, everyone was back working on it completely. So that small turnaround time is what I feel gives a major advantage for the team. And it's actually a very good point which has been inculcated in all the team members so far.
Right. And to be very honest, every moment was a big moment and cherishable for me. Every team member was equally important. Every moment was equally important for me. But at the same time, the key things that always comes to my mind is, despite all those challenges that we had, and let me just, try and draw a fine line between other competitions and this competition. It's completely different. It's sky apart. You can't really compare, because I even came from a Formula team. I have worked with that, so I kind of have an idea of both the worlds. But it's completely different, and the way that our team reacted, all of our 25, 28 members, because some of them were not able to make it to Los Angeles that time, but everyone has equally put in their efforts, and I was really fortunate to lead them. And they had so much of what should I say, the patience to hear me when I am angry, and to Aditya is laughing, so to hear me when I am angry, and maybe I'm never making them comfortable. And Neil is one of the examples. He used to be rugged, and all the time we used to send him here and there. So but despite all these, we were together as a team, and that is what made us special. And if I have to talk about WTF moments, one of them was when we actually found that our shipment from China is going to come 1 month late. And when it came, it was really not getting assembled. And that was the moment we thought, like, we are gone. Another WTF moment was when we were in Los Angeles and we had to take the pod from SpaceX to one of our alums who is 1968 passed out from IIT Madras. And when we met him and we shook her hands, we called him sir. And he used to say, "Don't call me sir, take my name." And when we actually talked about the age, he said, your father wouldn't have been born when I was graduated from IIT Madras. So those were a couple of moments I'll always remember.
Right. Yeah, I think that kind of sums it all up. Being a part of a student team is always something that people will cherish as part of their university days. And that's precisely the reason why we're having this webcast series where we have different teams like Avishkar here today. Basically, it's for you viewers to inspire you to be a part of these student competitions. Whatever you can get your hands on, whatever it is that you can get involved in to apply your knowledge. It's not just about learning things in class. It's about being a part of a team, believing in something together as a team, and most importantly, the people you work with will become like family at the end of the day. It's definitely going to be a connection that you will not lose. It's going to be engineering and friendship connections for life. So on this very positive and happy note, let's go ahead and end this session today. Thank you very much, Suyash, Aditya, and Neil for taking your time out of your schedule to be a part of this webcast. It's been great having you here, and I hope our viewers really enjoyed the session today. I know I learned a lot about Hyperloop from this past 1 hour. From my end, that's it. Thank you very much, guys. See you.
Thank you.
Hey, really, thanks a lot, Smeed, for all of this. Just a great opportunity.
Absolutely. It's a pleasure to have you guys.
Yeah, we had a great time talking to you. And
Sure. Great.
cool. Bye.
Okay. Bye.
Yeah,
Asher.
sure.
Yep.
Yeah. Is there anything else you want to discuss?
Yeah.